This is urethane reducer. We can pour this into another container, but this is the perfect size because this mixing chamber is half a liter, they said, ideally. Let's see, where does it say that? There it is. It can range from 2 liters with a preferred capacity of the order of half a liter. And that's for this mixing head. And this is 0.94 liters. It's right in the sweet spot, but well, but nothing. I mean, we could use this can as is, but I was thinking of maybe we should use this can as is, though. Maybe this can as is, actually. I don't know, it might be a little bit bigger than what we want, though. Let me get a spray paint can, we'll compare. But that would be a great base. I mean, we'd already be halfway done with the project. We've already got the mixing head picked out, and we chop off the top and bottom. I mean, that's the lid. It's got a lid on the bottom and the top. I wouldn't have to fabricate it. That's going to save us so much time. Then we just got to create the mixing paddles, and all the attachment points we can braze in. And then we just need to get the pumps and motors all connected. I mean, this is going to be quick, guys. Guys, this is even better, because they're almost the same size, but this one's a little smaller in diameter, so this is going to bring us down closer. Okay, so if this is 0.94 liters, then this one has got to be, well, maybe it even says it. It doesn't measure it that way, just measure it in weight. But 0.94 liters, this is, we'll say 0.7 liters. They said 0.5 is ideal, so we could just remove, you know, a centimeter or so from the height, and this thing's in there, boys. We're in there. Boom. You can see it's almost the same size. This is a little fatter, but when we reduce the height by a bit, I think that'll be okay. I'm thinking about it. I'm trying to visualize, because I'm looking at the ratio between the width and the height of the cylinder shown on my screen right now. That might matter because of the... As these paddles spin, from this motor on the top spinning them, these two reactants, which combine to form CO2 gas, need to be separated enough vertically with enough volume and width that they're being properly mixed in. This top one needs to be mixed in quite a bit as it travels down, and then this one get mixed in, and then in the bottom half the second reaction happens. The first reaction happens in the top half, mixing in the first reactant with the foam, which comes through this one. So molten polyethylene will come through this pump, through this tube, and into the top, where it will start getting mixed up by this paddle in a whirlwind. And then the reactant number one of part of a two-part chemical reaction, it could be baking soda and vinegar, or something else that when combined creates a volcano in a science project, for example. This one comes in and starts mixing in with the molten polyethylene from the first paddle, and as it travels down, it will mix in with the second reactant. And as these two reactants mix together, they form CO2 gas, and then that's what creates all the bubbles, and this thing's mixing really quickly, and this bubbly solution then starts pushing out through the bottom, and this valve can control the amount of pressure that's created in here as these are being fed. This thing's filling until it gets, we want an ideal approximately 30 to 60 psi of pressure inside this canister, and then it's going to push out the bottom, and this valve, depending on how tight you have it, will determine how much pressure will build up in here as it's being force fed by these three motors. Or no, these three pumps. These are going to be positive displacement pumps. I believe that's what they're called. Let's just verify that. They're hydraulic pumps. Yes. This is what it looks like. That's the inside of a positive displacement pump. And we don't want to pay $250 for this. That's ridiculous. So I'll have to make my own pump. That'll be super fun. We'll cut out these little star shapes with an angle grinder out of sheet metal. We will stack the sheet metal and glue it together until it becomes the thickness we want for these gears and height. And then we will just install maybe a little vertical shaft in the center right here, and a vertical shaft here. We'll slide it onto a vertical shaft. So there will be a hole in the center which we have to drill through our gears, and we'll slide it onto a metal vertical shaft coming out of the casing. The casing will have to probably take two pipes that are each round and then cut them right here and right here, and then create a flat piece of sheet metal to join the two in order to create this case shape. It's like two circles joined together to create this shape. And then we will solder or braze them all together. We'll probably use 2-inch copper pipe and copper sheet metal to join them. Then we'll use a copper top and bottom. We'll braze it all together, and a motor will connect to this, which will need to be welded to the gear, and then the top of this will come through the outer casing, through a rubber sleeve, which will be greased, which will allow us to turn it with the motor, which is placed outside of the pump, and that will turn this, which then will turn that, and that will drive the fluid through. And we'll need to create the two outlets, which we can use copper refrigerator line brazed onto our copper wall, which is going to be right here. And so this will be our solder bead, which is drawn by these two little flanges. And that's totally doable. We can create those pumps. You know, that's a couple days of work per pump. Totally worth it for the experience and learning and advancing our fabrication skills. So that's how we make these 3 pumps. This is just a standard motor. We've already robbed some motors from dishwashers and stuff. We'll be able to, or we could use the motor I just got from pulling out of the garbage, a little electronic scooter. It has a nice motor that would be maybe perfect for this. And this needs to go really, really fast in order to create a ton of bubbles that need to be dispersed evenly before it's spitted out through here into your mold. So that's how this machine works. That's how we're going to construct it. These will be copper refrigerator lines. Yeah, the copper lines that run from a tapping valve from your half-inch copper piping to your refrigerator ice maker are, I believe, 3/8 inch copper pipe. We can solder that onto our pump and then run it and solder it onto the top of here. These pumps are metering pumps. They can control the rate at which we feed in the two reactants and the molten polyethylene. All this piping will need to be wrapped in resistance wire, which is called nichrome wire, and electricity flowing through it to keep all this piping, the pumps, everything very hot. We'll wrap nichrome wire around this whole enclosure and run electric through that so that this will be kept at approximately 250 degrees Fahrenheit in order to keep the plastic at a molten state until it exits through here. Then it will begin cooling as it hits our mold. What is the melting point of aluminum? That's like, I believe 800 degrees Fahrenheit. The reason I knew that off the top of my head is because I was researching creating my own blacksmithing setup so I can actually do mold making. But what's great is I can actually fabricate all of this stuff with sheet metal. I don't need to actually do poured molten aluminum and create molds and casting or anything. Because I can actually stack and then glue sheets of sheet metal just cut out with the shears and then fine-tuned with just a grinding drill bit. I can just roughly fabricate these gears and smooth them out so that they all make good contact and everything. I can actually take this image, blow it up and print it out, and then trace, after cutting out these little star gears, I can actually trace them onto metal with a pen, and then actually cut it out with metal shears out of sheet metal, and then grind it really smooth and get it very accurate. And then I can actually test them out and turn the gears in my hand and make sure it's all smooth. And then I can cut out a bunch of them in order to make the thickness I want and glue them all together. And when I say glue them all together, I probably mean take each layer and sand it down and apply brazing, pre-tin it, and then heat it, and then they become welded together, so to speak, with brazing. Kind of like soldering two wires together. Or I could use actual epoxy. But yeah, actually, I might be able to use epoxy. I'm not sure. Will the epoxy lose its effectiveness when we heat up or send molten plastic through this at temperatures approaching 250 degrees Fahrenheit? Is there a failure point of epoxy at those levels? I don't know. I don't know if I want to risk that. Now, alternatively, we could create this. We could create these gears using clay. We could create a clay gear and then coat it in epoxy, cut the epoxy in half, remove the clay. We could even 3D print the gear and then coat that in silicone, cut it in half, remove the silicone. Now we have negatives. Now we can pour molten epoxy into that to create rock solid epoxy, all epoxy gears. Or that could break maybe. We could maybe 3D print these gears out of nylon. My 3D printer can run nylon. Heck, we could print the gears out of ABS. Because they're not long, flat faces, they would not fail. Although ABS and stuff, melting point is 300 degrees Fahrenheit. I wouldn't trust that. So no, we can't do 3D printing. I might trust epoxy not to melt. But it gets soft, and it gets more flexible when it's hot. I know that from experience. So I actually would prefer to make it from sheet metal, like I said, and grind it and stack them and solder them / braze them. But man, this is so totally doable, and I have all the materials. I have everything I need. I actually don't even need to buy anything. I'm telling you, nothing, nothing. I have it all here in my hoard. But I don't think it's a hoard because I've been saving things because I know I need certain things for machines I need to build.